Hey, this is Mr. Aiden. This is Physics Honors, and we're going to be going through what's called nuclear decay reactions. We're going to be taking a look at what happens when we have an element that is radioactive and what will happen to that element. How will it decay in terms of a nuclear reaction? And so the amazing thing is this, is anything that's radioactive, element number 84, polonium, and everything past polonium, those elements on your periodic table will be radioactive, which means they will spontaneously decompose, they will spontaneously decay, they will break down. And here we have, at the top picture, we have uranium. Uranium is element number 92 on our periodic table. It's got 92 protons, and it will eventually decay into lead. Element number 82. It's going to lose protons, it's going to lose mass, it's going to lose a bunch of different things. And it will eventually go from a radioactive element to a stable element like lead. Now, how does that happen? How does something break down just spontaneously like that? That's what we're going to go through today. We have a bunch of different types of what we call radiation from radioactive elements. The first one is called alpha decay. And what alpha decay is we have what's called an alpha particle. And we're going to do that by this little fish symbol, okay? And it has, this 2 means the number of protons. That's the atomic number. So it has 2 protons, and this is the mass up here. The 4 is the mass. So that means an alpha particle has 2 protons and 2 neutrons, which gives it a mass of 4. Okay? Now, some people will call this a helium particle because it's the same as a helium particle. A helium particle has 2 protons, 2 neutrons. It's got a mass of 4, and so you can, those sometimes are interchangeable. And so what you see here is we have a parent radioactive isotope, and this radioactive isotope, you can see what happens is an alpha particle breaks free and comes flying off, and you can see the parent particle is now become a daughter particle. And so what we have here is we have what's called alpha radiation. So you have uranium, we have 92, and we have 238. I'm going to give you an example of an alpha decay. So uranium is going to decay. It's going to decay into an alpha particle will come flying off. Now there's always a conservation of mass. So think about this like a mathematical equation. 92 protons is equal to what plus 2? Of course, it's 90, isn't it? And 238 is equal to what plus 4? It's 234. Uranium had 92 protons. It now has 90 protons, which means it's a brand new element. It is the element thorium, named after Thor. And that thorium now has a mass of 234 because out came a mass of 4, 2 protons and 2 neutrons, and that is called alpha decay. Now the amazing thing is alpha decay can't hurt you. This alpha particle is too big to even get through a piece of paper or your skin, and so alpha decay cannot hurt you unless you totally ingest it, and which in the mid 2000s or so, early 2000s, it was the way to kill people, was through alpha decay and putting it in their cup of coffee or their tea. Don't worry, alpha decay can't hurt you. So any kind of alpha particles, they're moving too slow, they're too big, they can't hurt you. Now we also have what's called beta decay. And what happens here is, and I'll give you the symbol for a beta particle. A beta particle looks like this. It's a capital B, but with a little thing. It's a Greek letter beta. And the beta particle, it doesn't have any mass. And it's got a charge of -1, which means this beta particle is just a high-speed electron. It's a high-speed beta particle, high-speed electron coming flying off. So we have a parent particle, and it becomes a daughter particle, and zoom, comes flying off a high-speed electron. Now beta can hurt you because this electron is going fast enough. It can break down your cells, give you cancer eventually, and so beta decay. So let me give you an example again with uranium 92 and 238. And so what do we have here is we have a high-speed electron or a beta particle coming flying off. And so Let's look at the top, the mass first. Let's go with the easy one. 238 is equal to what plus 0? Hopefully you can do that math without a calculator. 238. So 92 is equal to what plus negative 1? That's 93. 93, which means now it's a totally new element. And it's the element neptunium on the periodic table, is element number 93. Now, a lot of my students will just take this for granted and say, Aiden, yeah, sure, 92 equals 93 plus negative 1. But I had one student one year that said, Mr. Aiden, I understand alpha decay. We have a particle that has 2 protons, 2 neutrons. It comes flying off, and left behind is this simple thorium isotope. I understand that, but how can losing an electron make the number of protons go up? How does this happen? And it is a pretty amazing process. And so I'm going to kind of detail it for you right now. If you think about a neutron, what is a neutron? A neutron has a mass of 1. It's got a charge of nothing. Okay? Well, what's inside a neutron is we have a proton, and I'm going to put P for proton. And what do we know about a proton? A proton has a mass of 1 and a charge of positive 1. That makes logical sense, doesn't it? An electron, though, has a mass of relatively nothing. It is really, really, really non-massive. It's got a charge of negative 1. And so you can see how in a neutron, you can see how the mass, total of the mass, 1 plus 0 is 1. Total of the charge, plus 1, negative 1 equals 0. So a neutron is kind of made up of a proton and electron. So in what's called beta decay is a neutron kind of morphs and this electron comes flying off as a high-speed electron. And what's left behind is still that mass of 1, which means, do you see how the mass never changed? It had the neutron's mass of 1. It still has the proton's mass of 1. The mass hasn't changed. But now the charge has changed, hasn't it? Now, because that high-speed negative electron gets lost, the charge becomes positive 1, and what gets left behind is I have 1 more proton. And so what's happening in beta decay is a neutron is morphing, and out comes an electron. And that's what we have. It's a really, really, really neat process. It is pretty cool. Okay. So we also have what's called positron emission. Positron emission. So think about an electron, a high-speed electron comes flying off. Well, we have these particles which are called antimatter. And if you remember an electron, we just went over an electron. An electron has a mass of 0 and a charge of negative 1. So what is a positron? A positron is the exact same thing. It's the antimatter, a positron, and we put a little p for positron, and he's positive 1 and 0 and 0. And so we can have what's called positron emission, okay, which is no more difficult. 238.92, let me show you uranium, and let's say it emits a positron here. What plus 1 equals 92? That's 91. We still stay the same for 238, and we look at on our period table for the element number 81, and it's Pa, proactinium. Okay. Let's come to gamma emission. Now, gamma emission is the dangerous one. Yes, that is what made the Incredible Hulk green with purple shorts. Okay, with purple shorts. Okay, so I can draw a little bit of a Incredible Hulk here. Big arms, big legs there, big feet, big and so there you go. There's Incredible Hulk. Gamma emission. This is the dangerous one. This is the one that gives you cancer. Okay, when Hiroshima and Nagasaki, the bombs were dropped on them, the gamma emission gave people cancer. And so the amazing thing about gamma emission is this is the symbol for a gamma particle is 0 and 0. Okay? And you might say, how is that a particle? It has no mass. It has no charge. How is that a particle? Well, remember the wave duality of nature. It is a photon of light, of gamma radiation, which, if you remember, had such a small wavelength, such a high frequency, and such a high energy that that gamma radiation can give you cancer big time. So we have uranium-238, we have 92, and what do you know? You can see why this is dangerous. It's coming off very fast. Okay, now sometimes you have gamma emission that happens with alpha emission, sometimes gamma emission with beta emission, all these different things. We have one last, or actually two last types of our nuclear radiation, nuclear decay reactions, and here we have what's called an electron capture. And so here you have something like this. Let me give you an example. Again, we're just staying with uranium-238 and 92. And guess what? We captured an electron. Remember, what's an electron is 0 and -1. -1 in terms of its charge, 0 in terms of its mass. And what do we end up getting? We get 238. We end up getting 92 plus -1 equals 91. And so remember what 91 was on our periodic table. That was that Pa, that proactinium. And what do you end up getting? You end up getting an X-ray. So you end up getting some radiation in terms of an X-ray there. Not quite gamma radiation, but we could even just say X-ray radiation. We get some X-ray radiation there. Okay. Last but not least, we have spontaneous fission. Spontaneous fission, again, is breaking down. And what comes off is neutrons. Neutrons are going to fly into other ones, and it will continue to go over and over and over again. We'll talk about spontaneous fission in another video. It is really an amazing thing of spontaneous fission, and that is how we get a lot of our energy in terms of nuclear energy from spontaneous fission. Now, the amazing thing about all of this is that the decay is consistent. We call that the half-life. T1/2 is called the half-life. You can see here, the half-life of cobalt-60 is 5.27 years. So if you had 10 grams of cobalt-60 in 5.27 years, so about 5.3 years, guess what? You would have 5 grams of cobalt-60 because it would be decaying. If at 10.6 years, you can see another 5.3 years, it's down to 2.5. At 15.9 years, you're down to 1.25. At 5.3, 21.2 years, you're down to 0.625. See what happened? You had 100%, and now it's down to 50%. Then it went down to 25%, then it went down to 12.5%, and so on and so forth. And the half-life is consistent, and this is how we are able to do what's called radioisotope dating. And some of you guys just woke up and said, whoa, what, dating? Mr. Reed's going to teach me how to date? What? Radioisotope dating, we're able to take a look at something and be able to, using some assumptions, there are assumptions involved in this, is be able to calculate when we had 100% by going backwards. It's like a clock. It's like knowing where we are on this curve, okay? And so you can see this is an exponential curve. If you graphed it out, it would be natural log versus time, natural log of concentration versus time. Natural log doesn't mean anything to you yet, but it will in a few years, less than a few years. And the amazing thing is this is an exponential decay here, an exponential decay. And it is consistent. The half-life is consistent. It will continue breaking in half at every single half-life. And so cobalt-60's half-life is 5.3 years. This is why this is probably one of the most dangerous, if not the most dangerous concept ever devised by man, is a cobalt-60 bomb. Because guess what? It would take 5.3 years for even half of that to break down, which means we would all be dead in a nuclear winter before all of it was decomposed. We will never hit 0, though. I want you to see, we will never hit 0. We will never hit 0. It will asymptote here at 0. We'll never hit 0. But this also, we do this with what's called carbon-14 dating. I'll hopefully do a video about carbon-14 dating. And the amazing thing about carbon-14 dating, this carbon-14 dating shows that dinosaurs did not exist millions and millions and millions of years ago, 65 million years ago, because there is still carbon-14 in the fossils. Okay, and so the amazing thing is there are hundreds of ways to do radioisotopic dating and to find out how old things are. So that was nuclear decay reactions. I hope that was pretty cool, and I'll catch you on the flip side.